Today, we're going to learn about the secrets of printf. Today's video, we're going to talk about printf. And a lot of people who are new were the secrets of printf, but these aren't really secrets. This is how printf works. A lot of people who are new to C programming, they only see printf in the way they typically use it. And typically how it's used is, let's just create one. So we do printf, my name is %s, and I am %i years old, /n, and quotation comma, sz name, which is a character pointer or character array, comma, I age, which is an integer. So the first thing is that a lot of people think that I have to pass this string literal as the first parameter. It's not true. The prototype of printf is printf const char pointer psd format string comma dot dot dot, where dot 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 is variable parameters. I can pass any character pointer as the first parameter. It doesn't matter. I can pass in, I can do, on the as a local variable, I can do char sc format parenthesis 25, and I can do string copy this same string into sc format. We'll just say that dot dot dot, and I can do printf sz format comma sz name comma I age. Perfectly valid. Printf only cares about getting the first parameter as a string. It doesn't know, it has no idea it's a string literal or not. So a lot of people think printf is magic. And there's two magic potions that printf has. And the first one is that it knows whether you pass a string literal. It doesn't know. It just, the compiler knows whether you've typed it correctly. So if you try to pass an integer without typecasting to char pointer, it's going to flag you. But you can pass in an array or a character array or a character pointer into the first parameter. So you can runtime generate whatever you pass into printf. The second thing people think is the magic potion is that these the parameters beyond the format string printf knows. It already knows how many parameters you passed in and the types. And it doesn't. Printf and the programmer have a contract. The contract is that the programmer will tell printf what parameter, how many parameters there are and what the types are by specifying these format specifiers in the string. So as printf comes through and parses this string, it looks for these %s. And says, oh, you told me %s? I'm just going to grab whatever's on the stack and I'm going to try to display it as a string. And then he comes over to this I. Oh, okay. I'm going to grab whatever's on the stack above that and try to display it as an integer. If you haven't passed anything at all to the printf, he will still try to do that. And he will just try to do it with whatever random garbage is on the stack. If you reverse these parameters, he doesn't know. He'll try to display age as a string and your string as an integer. And the only time that this is a problem is usually with %s, right? Because %s is going to try to dereference a pointer. So the first address that goes in there, whether it's the integer or the string, it has to be a valid address. If it's not a valid address, then it'll crash on that first access. The second thing is when he tries to display the string, he's going to go through the string and print every single character, whether it's garbage or not, until he hits a 0. If he never hits a 0, he's eventually going to hit the next page from that page and keep going until he hits one of those next pages that's invalid, right? Because you only have so much memory. Eventually you're going to hit a page that's not valid. It's not there. So those are the ways he crashes. And so even if you don't pass any parameters, he just can grab whatever on the stack and start printing it. He doesn't care. There's nothing in printf that is magic. Now, he won't crash grabbing the stack typically, but if you put enough parameters on here that pass the top limit of the stack to eventually hit an invalid page, then yeah, you're going to crash there too. But he doesn't know what these are, so you can fool around. Now, one of the things is though that modern compilers, since the C library is standard and it's supplied by the compiler can't have intimate knowledge of the C library. And based on intimate knowledge, it can do special optimizations or special checking. Certain optimizations include, if he doesn't think that that function is actually giving benefit, he can remove that call altogether from the compiled code. Well, another thing he can do is type check. He can say, oh, you said %s here, but you didn't pass a string here. Or you said, you've got 2 parameters here and you only pass 1 parameter. So he can actually do the type checking and the parameter count checking for you, the compiler. Older compilers didn't do it. And if you wrote your own version of printf, it won't do it. It won't do it for just any random function that does variable parameters. It can only do it specifically for the ones that are supplied to it by the C standard library, because those are implemented in a standard fashion and have intimate knowledge, and the compiler can have intimate knowledge about them. That's the only way. But it falls short, because if I do this here, pass a buffer that's generated by the code, then he cannot do a type check. Especially if it's runtime generated based on different arguments and parameters or input from the user, and then you generate this string. He can't do compile time checking, and the printf doesn't do runtime checking. He has no idea how many parameters you pass to it. There's nothing to check that. So that is, in a nutshell, how printf works. So this video is in 3 parts. This first part here was to tell you the basics of printf. How printf determines how many parameters there are. That the first parameter is not special. It can be any buffer being passed into it. And printf does not know, type checking or the number of parameters. It trusts the programmer to tell it how many parameters and what types they are. The second part is I have written 2 implementations of printf purely in C. And I put them in the description below. So I'm going to go over those step by step. And so by reviewing those, I'm hoping to give you a better insight. Now, I haven't written the complete printf because I've only implemented %s and %i because it's just a demonstration. Secondly, I haven't optimized it. I directly keep printing every single character versus buffering them and printing them all at once. So it's not an optimized version. It's simply for demonstration, so you can get a more intimate knowledge of how you would implement printf, how you do variable number of parameters. Now the third section is going to get a little bit hairy. It's going to be more about culling conventions and how the stack works with printf, given it has variable number of parameters. So those are the 3 parts of this video. And so this is the completion of part 1. Now we're going to go on to the second half. Okay, so here is our program. Now we have 2 printfs. We have printf new, printf manual. We have our var arg declarations. We show that we pass in one instance the string buffer. We pass in hello, and we pass in the same to both these functions. Test string %s integer, and then we do double percents to test the percent string version, or the percent display, because printf has to display a single percent with a double percent, and I've actually implemented that. So let's look at the code. We return integer, which is the number of characters. We have character count of 0. Our print integer string, chart pointer. Now, to get the variable arguments, we have va list, and va start is a macro. The first parameter is this. The second parameter is the parameter before your variable arguments on the stack, so it knows where to start. Now we do a while loop, and we look at the character, the current character. Is it null? Then we're going to exit. If it's not, we're going to do an if is a %. Now we'll look at the not % first. If it's not a %, we're going to use put char. Now again, since I wrote this all in standard C, we can use standard C functions versus environment-specific screen output functions. So we just use put char, and increment our character count, increment the next character. Loop back around. Now if this time we do have a percentage, then we increment to the specifier portion, and we check it. Again, if it's null, we exit because we're done. If it's a %, we just print %, increment, character count, next loop. If it's none of %s or %i or % or 0, the default is just to print whatever it is. So we print the original %, whatever character's there, increment the format string, and add 2 to the character count because we're not supporting it, so we're just going to display whatever they specified as % whatever. Now, if we do %s, we're going to take our local character pointer, use va-arg, and specify it's a character pointer. So it's just basically typecast it for us because, again, the locations on the stack are untyped. So we're just typecasting it to that and giving it to the print. We use fputs instead of puts because puts a new line at the end of the print, and we don't want to do that. So we use that, print that, and standard out. We increment the format string again, and then the character count is obviously the string length of what we printed. Now we have an integer. In this case, we get it again, we pass in a type. This var-arg handles any increments along to the stack to the next parameter or whatever. Now we typecast to our local print integer. Now we want to print a string, so we're going to use integer to string function, or integer to ASCII, and we have our local string function. We're going to use base 10, and we use fputs again. Increment the format string and get the string with the character pointer. So, and at the end, you just say va-end. So that's how the first function works. And again, as you can see, it has no idea what it is. It's just parsing the string, and then as it finds whatever value's there, it just assumes that that's the next type and tries to print it as that. And that's how printf really works, and that's how we've implemented it. Now, printf manual is exactly the same code. The only difference is I manually, instead of using these standard arguments, I've manually implemented it. So I get the stack location of this, so I get the address of that, which is the address of the stack, and then I increment the stack to the next location. So I get the next parameter. So for that one there, I would end up going here. And that's done by typecast. So we typically have stacks that are the size of the maximum size of the virtual addresses on the platform. So that means that a pointer is the size of the stack, which means the size of a single stack entry, which means if I do void pointer and try to increment it by 1, it's not going to know what to do because there's no size of void. And if I do char star here and increment it by 1, if I actually increment it by 1 address location, not a stack location, I would have to increment it by size of character pointer if I had a character pointer here to get this correct size of the address to go to the next place. Or, as I've done here is, because whatever you increment here is going to be the size of whatever this points to. So if I increment it by void pointer pointer, it says this is a void pointer pointer, which means that this holds a void pointer. And a void pointer is the size of the platform's address. So just doing stack address of void pointer pointer, and then increment by 1, I get the next stack location after format. Now same code. The only difference here is instead of that macro, I'm doing this manually. I have my same increment after I use it, but I'm just typecasting that stack location. Since I'm holding a character pointer at the stack location itself, it must be a character pointer pointer. So then I give character pointer pointer to the stack location. I then dereference it and typecast the character pointer, put it in the character pointer string. Same thing with integer. Since the stack location is now holding an integer, the stack location itself must be an integer pointer. So I typecast it to integer pointer, dereference it. Again, this typecast is redundant. You don't need it, but I have it in there anyways to be explicit. And again, the next increment. That's the only difference between these two functions is I've now manually done the stack walk. So you can see how the stack walk works. So, fairly straightforward. And as you can see, you can perfectly implement this fairly easy in C. And so now on to the part 3. We will talk about a little bit more in depth on the calling convention itself of printf. So today we're going to talk about calling conventions. Now in the future I may have a video that is more in depth on calling conventions, but today we're just going to talk how it relates to printf. Now, first of all, we got to talk about the general concept of calling conventions. So calling conventions is basically a contract between the caller and the callee. And the contract has three things. First thing is how the parameters passed to the callee. Is it on the stack? Is it in certain registers? Where is it at? Right? Second thing is who cleans up the stack if the stack is allocated? Is it the callee or the caller? And the third thing is how was the return value passed back to the caller? What register is it in? So those are the three things. Now today we're going to talk about specifically how it relates to printf, and more or less not really how it relates to printf itself, but just how it relates to variable number parameters. So I've created these three stacks here. Now, in general, how caller to callee works, and I'll put it in here, is that there's two methods you could do. One is you push the parameters on the stack from right to left, or you do it from left to right. Like Pascal did it from left to right, which means that you do push, first parameter stack, then you do push the second parameter, and push the last parameter. And now this would generate, then you have the return address. Oh, this is Pascal calling convention. Now, C calling convention was the opposite. You push the opposite direction. So you push the last parameter first. All right. Push that. Push that. Why it's doing that. Oop. And then you push the first parameter. And then, of course, return address. Now, we can actually show that here in this stack diagram that I have. So, Pascal, if we had ABC parameters, we would, in Pascal, push A, B, push C, the return address. C would be the opposite, right? C in standard call, C, B, A, red address. Now, as you can see here, whenever the function goes into the caller, your stack pointer is here, right? So your stack pointer is at the return address. So if you had variable number of parameters and you're using parameter A to parse those parameters, as you can see here, I have no idea how many parameters it is to get to A if they were pushed on that way. If they're pushed on this way, I can get A, and then I can start finding the parameters as I parse A. But here I can't. So this one here is a problem. So you can't use variable number parameters with this type of calling convention. Unless you did something really weird, for example, like this. You put the parameters on backwards. If you put the parameters on backwards, which means that now you're saying arg0 goes here, 0 goes there, or here. So if you did it backwards, it will look funny. It'd be hard to do. We'd be trying to figure this out all the time, put these parameters, variable numbers on first before you get to your string, because then if we did it that way, then yeah, sure, you would be able to to parse it, because now C or D or whatever the last parameter was will be first, and you'll be able to parse it. But now you've got to program in this fairly awkward manner. And so that's the first thing, is that you push the parameters on right to left, so that this one is the bottom of the stack. And so now I can just go to that because I know it's there, and I can parse it and get the correct values. So that's the first thing I wanted to talk about. And the second thing I want to talk about is there are, for example, in 64-bit, in x64, the first parameters are in registers: RCX, RDX, R8, R9. And so you may be wondering, whenever I come down here and I get this address, right, the stack address, how am I getting the address of a register? And the answer to that is simple. Is that, for one, the compiler has to take care of that and emulate it or do something to make sure that it can give a proper stack address, or give a proper address, or emulate it somehow so that this does work, because this is standard C. The second thing is that the C 64-bit calling convention actually requires that there are 4 stack allocations. Let's see, stack allocation 4, reserved. Reserved on the stack for the function, for the call E to use as scratchpad, or to save. It's called the home, so it can save these registers. So while these are passed in there for fast access, if they actually need to save it, they don't have to allocate stack. They can just move RCX in location 1, RDX location 2, wherever he wants. Beyond stack 4 is actually, if there are more parameters, it's parameter 5 and so forth. But these are just garbage or blank. They're not used. They're passed. The parameters are passed here. So what it can do, for example, the compiler can do, is it can move RCX here. It can move RDX here. It can move these here and take that access hit because the program is asking for it, right? So, for example here, if we look at this here, and we unassemble printf underscore manual, that's exactly what it does. You see, it moves RSP into R11, and then it moves RDX, R8, and R9 into the stack location. Now it skips RCX because in my manual function here, as you can see, I immediately skip to the next stack location, and I don't use that stack location, so it doesn't populate it. However, if we look at when we use a standard function, it must only directly point this to that stack location and not increment it until you get in here. And so since it's an unknown of how it's going to be used, they actually put all the parameters on there. Or however those macros are implemented, it actually must save them all. So that is how that works. That's how they account for that. So the next thing we were going to look at is actually the return. So in 32-bit, we have cdecl. We also have standard call, where standard call will clean up the stack. However, if you use standard call, it's actually ignored on variable number parameters, and it reverts back to cdecl. And I actually have a bogus function down here that has a standard call that we can use to see what standard call actually looks like. And in fact, we're just going to program that in here. We're going to program in standard call, and just put it in a bunch of times. We're mostly just just trying to make sure that it gets called and doesn't get optimized out. So that's what I'm putting in here a bunch of times. So now we're going to compile this in 32-bit, see if it actually works. There we go. And so now we're going to do SLO printf underscore new. Whoops. We're going to the end here. As you can see, printf does ret. So there is a C2, this is the opcode here, a C2 version of ret, that takes a parameter of a word that tells you how many bytes on the stack to remove when it's a standard call function. And so that one is actually not a standard call. So standard call is a standard call. You see, I've asked for parameters to it. So if I take a look at that one, as you can see here, it actually does do C2 and then does the word to remove 12 bytes from the stack, which is 3 parameters. In 32-bit, 4 bytes each. So that one there is standard call. This one's not. But now think about it. How would you implement standard call with variable number parameters? Well, one way is to dynamically change these bytes here before you exit. Now this is self-modifying code. The problem with that is if I'm here and I modify this instruction, by the time I get there, since it's only a few instructions away, or if I do it right here, if I do that modification, I may not execute this instruction. What I may execute is the old instruction. And I did this test a long time ago on a 386 and a 486. The 386 actually executed the modified version. The 486 executed the old version. That's because they don't do a fetch of the instruction each time. That's too slow. They do a pipeline. So they bring in a bunch of instructions at a time and start parsing them. So if that one's already in the pipeline, the old one, it's not going to see the new one. So in order for that to work, now you got to flush it out. So now you have to do a flush, get that old value out of there, and cause a refetch. The problem there is now, I mean, obviously you're getting a lot more time, but so now you have to do that, do some kind of fence or some kind of call to make sure that you flush it out so you get the new value. The problem is not multi-threaded safe. So you're like, okay, well, I can throw a lock in there. I do a lock, you know, right? So now I'm looking at this, I'm saying, okay, so I'll do lock, modify, you know, but I can't unlock after the call, so I have to unlock within the function itself, and then so then I do ret. So now I'm thinking that, okay, if there's another thread at the lock, right, when the modify happens, or when the unlock happens, I'm thinking that I should be able to go fast enough and get out. Or if he does do the modify, that this is still in my instruction cache long enough that even if he did modify it, I still have the old value. However, if I took an interrupt between these two, then that's all bets are off. That's not gonna, right? Because now if I took an interrupt, I'm probably gonna get the new value. If I take an interrupt, right? They modify, so now I'm gonna have the new value. I'm gonna crash. So this doesn't work. So now you're like, okay, what else could I do? Well, perhaps what I could do is I could, for example, move data, like sample EIP. So now let's say I know, you know, I'm at, you know, ESP stack pointer is equal to the return address. So that means ESP plus 4. So then I move ESP plus 4, you know, C2, and then, you know, move, you know, ESP plus 5, 5, you know, word, the size to remove, and then I jump to ESP plus 4, and so that way it's per thread, because I've now modified the first parameter, so I don't need the first parameter anymore. I can throw it away, and so now I can modify that and then jump to it. So there's still a problem with this, in that now your stack needs to be executable. And typically you do not want your stack to be executable, you want it to be non-executable, which protects that if you have a buffer overflow that injects code onto the stack, if they try to jump to and execute that code that's been overflowed onto the stack, it won't work. Right, so you don't want your stack to be executable. So that kind of throws this out the door. Now, remember what I talked about before about conditioning, where you're looking at one thing, this is how this is done, and so that's the only possible way it could be handled? Well, it's not entirely true. A lot of times, what could be done, for example, is you modify the stack frame, right? So if you create a new thread, for example, you're going to return to that function. I mean, the OS is always, in certain places, certain code places, it will set up and create stack frames, right? Exception handling, for example. And if you want to continue, modify registers, it's got to modify the stack frame. Now, typically, the compiler does not do that in regular flows. But if you really wanted to have a callee-based stack cleanup for variable parameters, so whenever this callee knows where the last parameter it perceives is, it could copy, the return address, right? It has to use a volatile. It doesn't have to. It could save registers, but best to use volatile. So perhaps it moves ECX to ESP as a return address, and then it moves ESP plus whatever the last return address was, or last parameter was. It moves the return address there. Then it moves the stack to that location, and then this is a ret. It could do that. The only issue there would be if you passed more parameters or less parameters than you actually had, then you wouldn't really be cleaning up the step appropriately. But you could say that's still a programming bug, and if they're going to crash, then later on, who cares? Instead of letting it gracefully ignore that situation in some cases. So, but this could be done, and so you could do that. Now you're slowing this function down, but again, it's a variable number of parameters. You already have pushing parameters on the front for the stack in 64-bit, so you are doing this. But again, this is not what happens. As you can see, what happens is you are forced to use a caller-based cleanup calling convention. So that's how it's used, and that's why they do that, because it's easier. Instead of doing this type of stuff, I mean, you can't do self-modifying code. It's ridiculous to do it for this, and I don't know, it's doable to do the stack modification, but it's not something that they're going to want to do. They're just going to keep it simple and say, hey, if you're using variable number parameters, number one, you have to have a right to left push of the parameters, and two, you have to have a caller-based stack cleanup. And so that's what they enforce, which is C calling convention. That is a standard C calling convention. And so that's a little bit of an in-depth look into how these are set up. Again, that is completely ignored. It doesn't even give you compiler error. Just completely ignores it and gives you the C decal calling convention. So, in a nutshell, that is the secrets of printf.